Having discussed what waves are, now I want to talk about how we represent them mathematically, both algebraically and graphically, so that we can do stuff with them in physics. Note that representing a wave is going to be complicated. We need to know the state of the medium at all points, and we want to know this at all times. If we pick a fixed moment in time, we create what's called a snapshot graph, because it's like a snapshot of a picture. The idea here is that we plot the shape of the medium as a function of position along the medium at some particular moment in time. Alright, so we say that we take a flash with our camera and our string or whatever is distorted in this shape at that moment. This tells us where each point in the medium is at that moment, but it doesn't tell us anything about how that changes with time. In fact, even the addition of saying wave speed with this arrow is a bit unfair because the snapshot cannot tell us which way the wave is moving. So we might also want what's called a history graph, which shows the motion of a particular point at various times. We build them pretty easily by taking a series of snapshot graphs and looking at the same point in each of them. So here they've picked this point x1, and they say at the earliest time it's a little bit up, and then it's a little higher, and at the later time it's a little bit lower again, and then it's back to 0. And we map them into their place on the graph, and we find that it looks like this. You'll see, by the way, that the graph looks similar to the input graph. Looks similar to the snapshot graphs, and that's not surprising. Consider this snapshot of a wave located right of the origin but headed left. Which of these is the correct history graph for the black dot at the origin? Well, we see that as the wave moves over, the first thing that's going to happen is that as this pattern says that this is going to go up, the dot's going to go up a little bit, then it's going to ride this all the way down. It's going to come all the way down, and it's going back up. So we're looking for a thing which rises a little, goes much less lower, and comes back up. That is to say, we're looking for A. Alright, the sense of the disturbance is called its phase. We'll get a more direct and precise definition later. As usual, which is considered positive and which is considered negative is arbitrary. Although we often talk about the phase of a wave, really the phase is a property defined at every point of the wave. Media don't extend forever. When one medium ends, another begins is called a junction. If the medium ends and the waves can't go any further, we have a terminus. When waves encounter junctions or terminuses, they reflect, reversing direction, but they may also invert, switching their phase. Here we have what's called a free end terminus, because we're going to generate the wave at this end with our source. It's going to move along here. At this end, this dot is connected loosely to this rod, so it can move up and down. All right, that's the end point of it. But there's no wave medium beyond, so the wave can't go through that point. It does have to end here, but this point can go up and down. And what happens when we do that? Let's see with some triangle pulses. We see that we get a wave that has reflected because it's going backward, going leftward instead of rightward, but it has not inverted. It's the same phase. Why? Because in lifting this thing, it pulls up on the ones next to it, generating an upward pulse, which then moves that way. Let's see one last time. All right, this thing shoots way high, yanking these guys up and causing a backward pulse. The key insight, though, is that that pulse traveling leftward is of the same phase. It's still above the split line. In contrast, here we have a fixed end terminus. Now, the end of the wave, the ends of the device, there's still no medium past it, so it can't go any further. But this point cannot move. Does that have an effect on the wave? It certainly does. So here's our inbound triangular pulse. But when it reaches here, this point cannot move, and so we get an inversion. Right? It reflects backward towards the left again, still a reflection, but of opposite phase. Why? Because to hold this in place, the device is pushing down. And of course, if you push down, you would generate a downward pulse. This distinction between fixed ends and free ends is absolutely crucial, because in the free end, we get no inversion, and in the fixed end, we get an inversion, and that will end up playing a big role when we talk about resonances. Alright, if we create a wave by disturbing the medium via simple harmonic motion, we get a harmonic wave. Harmonic here again comes from the fact that pure tones have this shape and they sound harmonious. They're what we find in music. In this case, we can write a simple wave function that reflects the state of the medium at any point in space at any moment in time. It's traditional to use the Greek letter psi which is this thing, which stands in for whatever kind of wave the wave is. For a wave on a string, it's the displacement of the string. For sound waves, it would be the pressure at that point. For light waves, it might be the electric field at that point. This equation gives a wave traveling in the plus x direction. For a wave traveling in the minus x direction, we would use minus, we would switch the signs here. So what do we have? We have a cosine, and it's an argument of both x and t, space and time. It has some amplitude, just like before. And then it's 2 pi times the ratio of x to the wavelength minus 2 pi of the time to the period. It's possible if you look around this and you factor out sort of a lambda out of this, then you would get lambda over t on the top, and you'd pick up that v. So people sometimes write it this way as well, x minus vt, where this is now how fast the peak is moving. So here's a simulation on Desmos, where we just take the wave function. Desmos doesn't let us use psi, so I'll use f, and I use that alternate variant there, and specify some, in this case, arbitrary wavelengths and amplitudes and periods and so on, but then we fake a time thing. So this plots it at t equals 0, and then we'll let t increase between 0 and 25 to see what happens to the wave. And what we see is that we see a wave moving to the right. So this equation does in fact give us movement to the right. What's going on here? Well, at t equals 0, I'll try it one more time. At t equals 0, the peak is here, but as time goes on, this term gets larger. So x, which is the location of the peak, must also get larger. So we have to have it going that way. That's why the minus sign implies rightward. All right, these waves all have the same wave speed v. The horizontal scale is the same for all graphs. Which wave has the highest frequency? Remember that v equals lambda f, and v is constant. So high frequency implies low, or small really, short, lambda. So I want things that have low wavelength, which would be b. Which could be the correct equation for this wave, whose speed is 0.4 centimeters per second. Well, we see that the amplitude, which of course is the distance off equilibrium, so here, that's 4. So these guys are both out. And then we can see that the wavelength, which is the space between here, well, it goes out to from just shy of 5 to just shy of 7. That is 2 centimeters, so we end up with this. So it must be this one.